All right, last one, folks, from 0654, winter 2019, paper 4-2, question 12. Fishing boat floating on the sea. We've got a heavy anchor dropping from the boat, accelerating as it falls through the water. Name the downward force that makes the anchor accelerate. We go for weight here. Now, some people write gravity here. I would stay away from that. Gravity is what causes weight. Okay, gravity is a concept that we use to describe why weight happens. However, it is not a force. Okay, if you want to get the word gravity in, then what I suggest you do is write this: the gravitational force. All right, I would always be a little bit wary of using the word gravity here. Okay, we've got a generator, and we're being asked to label slip rings. Okay, 2 slip rings right here. You only need to label one of them. I've labeled 2 because I'm annoying like that. All right. As long as you remember the letter R. All right. Some people forget that. Describe how the use of slip ring produces an this is hard. Produces an alternating voltage from a rotating coil. Let's have a look at our demo here, our picture here. We've got each of those slip rings is connected to one side of my coil. All right, so if you notice here, this one here is connected to the right-hand side, and then we've got the left-hand side as it currently stands. Okay, those rings are going to rotate as my coil rotates, so they all rotate together. And what we have here is some little brushes. These are called carbon brushes. They're spring-loaded, and they just produce a nice, gentle connection to the ring. The coil rotates, bringing the rings with them. Those rings then conduct the electricity out to the external circuit, okay, via contact here. Okay, let's think about why it produces an alternating voltage. Where you think about it here, when I'm rotating, let's imagine we're doing a clockwise rotation. This side is moving up, and this side is moving down. However, when they get to the other side, those directions are going to reverse. All right, we would have side A and side B. Side A is moving up, and then it'll be moving down, up, down, as it moves round in this rotation. Okay. Side B starts off moving down, and then it's moving up. Then it's moving down, then it's moving up. Now we saw before that when we're generating an EMF, the direction of the current really depends on the direction I cut. So every half turn, we're cutting in a different direction, and therefore changing the direction of the EMF. What have I written down? Each side of the coil is attached to a slip ring. Okay, that's very important. The wires cut the field lines in different directions during each half turn, and this produces or induces, better word, a voltage with a changing sign. Okay, this is not a full description, but it gives an idea of why it's changing. The whole idea there being that as you cut in different directions, the direction of the value or the sign of the EMF will change. Okay, sketch a graph of voltage output against time. I've deliberately not done this here because I want to do it live for you. Okay, I've got my pen here. I'm almost definitely going to make a mistake, but that's life, right? The way that I've done this, you can see I've set it out for myself first. You need to be drawing a sinusoidal curve, okay, and it needs to be well drawn. What have I done then? I've divvied up the page nice and simply. I've taken each big box and decided that one wave will be 4 boxes. Okay, so that means if I start at 0, then I get to the first box, I'm going to be at maximum. Second box, I'm back at 0. Third box, I'm at minimum. Fourth box, I'm back at 0 again. What I now need to do is I need to trust my graph drawing skills to be able to draw something which vaguely resembles a sine curve. I'm pretty happy with that. All right. Key points here: it's a sine curve, not a triangular wave, and that we've got these A values here which are constant. Okay, you have got a constant amplitude all the time. Please make sure that that is always there, and be careful with it. Use the whole bit of paper if you can. All right, certainly from left to right. You could extend it up as long as you extended the bottom one as well. Okay, electric heater on the boat. We're told 240 volts. Might as well label that as V. We're told a current 20 amps, and we're told a time 1 hour. Remember, your hour has to be in seconds. Okay, so I've gone straight off and said 60 minutes times 60 seconds, 3,600 seconds. Okay, I then look at the question. Okay, a couple of things actually going on here. It's a 3-mark question, all right, which suggests something else there. Okay, a bit more complexity. There are additional complexity that we've just talked about in calculating the time, but also in stating our unit. This is a unit everyone forgets, don't know why. Okay, you don't need to write down the name of the coulomb. You just need to write down the unit, which is C. We're saying Q equal to IT. Okay, 20, which is our current, times 3,600, which is our time. We've got 72,000 coulombs. All right, last one, just to finish off. Okay, we are using a set of binoculars just right at the end. It's amazing the sort of stuff which gets fit in to these questions. I'm just hunting around for my ruler because I want to do this for you guys. We've got a pair of binoculars looking at the sea, and we're using glass prisms to reflect the light. Now, careful here. Key point about this is that we're using glass prisms, not mirrors. Usually, we would assume that a mirror is going to be used for reflection. Here we're using prisms. How does that work? Well, we've got a light ray entering, and you notice that it's entering our glass prism at this point. It gets to here. Now, a common mistake that a lot of people make is they have the light bouncing off this point, whereas actually the diagram already shows you that the light is passing through into the prism. The reason it's passing through is it's because it's traveling along the normal. All right, if it travels along the normal, angle of incidence is 0, angle of refraction is also 0, just pass through. Then what we've got here is something interesting. We've got it meeting the light meeting an interface between a fast and a slower medium. And that's where something is possible. It's called total internal reflection. And that's what we're relying on here. What we're relying on, is this light to be reflected down, okay, then back to left, and then back down again, and then out. Okay, you notice you've got the ending here. What you have to do is really join the dots. Now, this is one of those instances where you could just think, well, I have to join them up. What's the way I could do it? This is the way we can, all right? You could also be understanding how this works. As I've mentioned before, the reason there's no refraction as we pass from here to here, in and out of our prisms, is because we're traveling along the normal. And the reason that we've got total internal reflection is because this angle of incidence is greater than the critical angle, and therefore you've got reflection. Okay, these two angles, by the way, should be the same, and again and again and again. All right, you don't have to add all this, but I'm adding it so that we can kind of understand it a little bit more. Note, it is a 1-mark question, so you're not expected to do much more with this, but I have seen people struggle with this quite a lot. The reason being is because they think that this thing is a mirror when it is quite clearly labeled as a prism. Okay, so be careful with those drawings, be careful in reading those instructions when you see a question like this.